Okay, it's almost about 2 o'clock, so I think it's time to start the tutorial, and I leave the floor to Len Dissado and John Foggy. Len, John, please.
Thank you. The title of the tutorial is, as you see, Why and How do Polymeric Dielectrics Conduct? And I thought that this was an appropriate question to ask in the city of Galvani. You'll find this statue in a small square behind the Cathedral San Petronero. First, I'm going to give you a grand tour of the talk. And I'm going to start off by reminding you of some very simple things that we all know and perhaps take for granted. And I'm going to move on to there and say something about the origin of low field conductivity. And this will merge naturally into the nature of charge carrier traps in the materials that we have. As we go towards high field effects, we've got to start looking at injection mechanisms, carrier concentration and transport, the effect of high fields on these properties, and that will start to bring us over to the effect of space charge on the current voltage characteristics. We'll move over from formal theoretical ideas about this property to reality and some of the recent calculations. Finally, I'll end up talking a little bit about charge packets. Now, for those of you who are unfamiliar with Bologna, Bologna is originally an Etruscan settlement. This is an Etruscan chariot, this is an Etruscan bronze warrior, and one of the major objects of art in Bologna is this statue of an angel by Michelangelo. Here we have one of the mosaics we'll be seeing on Wednesday in San Apollinare in Classa, and this is the major feature of Bologna. Everybody will recognise the two towers. I'm using this screen mostly because the other screen has a shadow on it which is a little bit disconcerting. Now, we're all familiar with the uses of dielectrics, and these are just a few examples. Dielectrics, ideal dielectrics, should not conduct. This is what we would really like to have, or perhaps we think we would really like to have that. And because of this property, we can use them for capacitors. They work as capacitors because they allow us to separate charge and store energy. We can use them as insulators. They isolate the high voltage conductor from the outside. And here we have another example of an insulator outside, separating high voltage from the ambient. In all these cases, polymers are one of the major materials that are used. Here we have a dielectric sandwich, two metal surfaces with a dielectric in between. We can store charge on the surface by charging it using a source of energy, a battery. And when we switch the battery out to the system, the charges remain on the surface, opposite polarity, positive charge, negative charge, and because the charge is separated, and we all know that unlike charges attract one another, because we've separated them, we've stored energy in the system. The energy stored, well-known expression, depends upon the amount of charge you can store for a given potential difference. And the important dielectric property relating to this is the relative permittivity. Cable insulation is the conductor, the conductor is 0. When we move inside the insulation, the field goes up to a high value, and then because of the insulation drops down to a low value at the outer edge. Sometimes this is earthed, so there would be a discontinuous drop to 0, but in many cases it's not earthed. There is a discontinuous increase, and then it tails off in the outside, the atmosphere usually. And the important thing here is that the field at this point is proportional to the relative permittivity times the maximum field. So if we think about these two situations, first of all, we don't want anything that will conduct. That will allow these charges to flow across the material, neutralize, remove our energy. But for a capacitor, we need a material with a high permittivity, also a high breakdown strength. For cable insulation, we need a material with a low relative permittivity. Now, I've said that the ideal dielectric is a material that doesn't conduct. So we have to ask the question, why do we think that is the case? And the answer is in this diagram. This is a calculation of the energy levels in polyethylene crystal. So these are the polyethylene chains are lined up perfectly in a nice ordered pattern, and we're not talking about amorphous region here. What you find is there's a large number of states which are full of electrons, and these electrons hold the polyethylene chains together. They're part of the valence binding of the chains. And because the polyethylene is a molecule, it's quite difficult to remove an electron from those states. It costs a lot of energy. And the amount of energy it costs, the minimum amount of energy, according to this calculation, is about 6.5 electron volts. And these states here are states with very little electrons in them, almost none. And they are states which extend through the crystal region. So any electron we put in here can move through the crystal region. And they are the states in which the carrier, the electron, is mobile. If we can lift an electron out of these states down here, they're called the valence states, they leave an absence of an electron called a hole, and that hole can move along the chain. It's not a real particle. It's limited to the chain. So if I move one electron from here to there, I create two carriers. This region here, called the band gap, and in a perfect polyethylene crystal with no impurities, no irregularities. There are no states in the band gap. Now we can do a simple calculation. The probability of finding an electron in a given state is determined by the Fermi function. And if we multiply by the density of states, that's the number of states per cubic meter, we will get the number of electrons that exist in those states per cubic meter as a consequence of the thermal promotion of the electron from the valence state. Here's a rough number. It's based on something like a density of states of 10 to the 28 per cubic meter, but because the band gap is so enormous, this number is very, very small. What it really means is that you need to have 10 to the 40 cubic meters of polyethylene before you could actually be certain to get an electron free to move through the material. So, according to this kind of calculation, we're reasonably happy that we treat these materials as non-conducting. This is really, truly an insignificant number, concentration of carriers. But this is not the case. Real dielectrics do conduct. And this is just to remind you of the relationship between the current density and the field, that is given by the conductivity. Here's a plot of experimental data, log scale in both directions. Y-axis is the current density, x-axis is the field in kilovolts per millimetre. What you see is the current here in this region. It's very small. It's there. It can be measured. It's normally regarded as ohmic, although the number of times we make a measurement in this region and find a current density that is proportional to the field is not so often. It's not so common. And then at some field, everything changes and the current becomes very strongly dependent on the field. These are plotted as power laws, so this would be J proportional to the fourth power of the field. So we do have some conductivity. And what's more, the conductivity is strongly field dependent. And here is the crux of the matter. This is a typical service range, particularly for cable insulation, and it covers the region where we go from low field conductivity to high field conductivity. The electrons don't have to reach the conduction band. They only have to move to the trapped states in the polymer. But the big difference now comes if we have a positive potential. What the positive potential does is transfer electrons from the filled interface states into the metal. Now we can lift electrons from the valence state into empty interface states like this. Doesn't cost as much energy as we had for the contact charge. So in this case, both cathode and anode will act in a symmetrical way in terms of injection. So we have the three ways in which we can get a charge density, a sufficient charge density into the polymer. Now we have to ask, how do the charges move once they're inside the polymer? Here, just for completeness sake, I've defined mobility in terms of the drift speed. That's the average speed at which the charges flow as they move through the polymer, and the field. And this proportionality factor is the mobility. So let's look at an electron coming along here in some sort of transport band, conduction band, quite happily moving along in a long extended state. This is a bit like me walking on the front. There's nothing in my way. If I was up there, I would have to walk along, jump over somebody, walk along, jump over somebody, just like you would have to do if you were at the theatre finding your seat. After a while it will drop into a trap. It gives up energy when it drops into the trap, and in order to get out it has to get that energy from the heat bath, the thermal bath, the temperature. So it takes some time. And the deeper the trap, the longer the time for the charge to get out. So the charge will come along, drop in here, may remain there, millisecond, drop in this one, that it's in there for a week or more, and so on. So the speed is actually governed by how long the carriers stay in these trap states. In between, it moves a bit like a metal. It moves so fast, it's as though it's no time at all. The hole does the same thing, except the hole traps are energy states above the valence band. Basically what happens is the hole comes along, these have got electrons in them, electron drops into the hole, fills it up, and you've got an absence of an electron here. In order for that to move further, we've got to take an electron out of the valence band and put it in that state. Then we've got a hole which can move again. Here, the trap states are states that have got no electrons in or one electron in. With one electron, you can put another electron in that state. There's a kind of rule of thumb definition. It's nothing like the kind of definition used in semiconductors, but we divide the traps into shallow traps and deep electron traps. So there are some good physical reasons for this, or rather chemical reasons. And if we look at the energy distribution, here's a kind of distribution in space. You see the shallow traps are empty states lying below the transport level. The deep traps lie a long way down, maybe here less than 0.3 eV, here anything 0.8 eV or deeper, and here are the hole traps lying above the valence band edge. Same kind of thing, the deeper traps lie to higher values and they're full of electrons. Now I'll say a little bit about the transport of holes, because what I've been showing you in the previous slide involves the hole moving by being trapped and then an electron removed from a chain in a different place into that trapped state. That's an activated process, and it's perfectly viable. And that's described by this phrase here. But we've got a different way in which the holes can move. They can move by quantum mechanical tunnelling of an electron between chains. Here you've got a diagram courtesy of John Lewis. Here's a polymer chain. This little white dot is the hole coming along. If I can take an electron from this chain and tunnel it into that chain, I'll get a hole in this chain. The expression that we find for the mobility in this case involves a number of factors. This one here is the tunnelling factor. It comes from the overlap of the wave functions on the two chains. Alpha is the tunnelling coefficient. A is the separation, the distance over which the electron has to tunnel. So you can see that this drops exponentially with distance. This thing here is an activated term. What it allows for is the fact that these chains are in continual motion. And so the separation between the chains is continually changing. This activation energy is what is required to bring one part of a chain close to a neighbouring chain. And this term reflects the fact that the hole wants to move in the direction forced by the field. It gains energy if it moves as the field tells it to. If it goes in the opposite direction, it costs energy. So the cinch term gives us the difference between the forward motion and the reverse motion. A over 2 is half the hopping distance or the tunnelling distance, and this is the energy gain or loss depending on the direction in which the hole moves. This is just a factor reflecting the speed or the probability per unit time of the process. If you put in typical numbers that tunneling coefficients are reasonably well known these days, what you find is that the tunneling is effective when the chains are about a separation of 1 to 5 nanometers, even closer. But you can't get much closer than about half a nanometer. Half a nanometer, 1 nano is 10 angstroms. Can't get much closer than about 1 angstrom, a tenth of a nanometer. But it's not necessary. We can still get good tunneling if we go a distance of 1 nanometer. So this is an additional process which is available to the holes. It occurs because the hole isn't a real particle. It only exists on the chain. You cannot put a hole in a cavity. You cannot put a hole in free volume. It must lie on a chain. So that's saying something of the general picture as to how the carriers move. Let's be a little bit more particular. Here's a semi-crystalline polymer. The crystals are thin plates, much narrower across the plate than they are in width or in length. They're represented here by these grey bars, and what you find is the polymer chain is very long. It moves into the crystal and curls around, but it can move between different crystal plates. It can move into the intermediate region where other chains are located. They knot together, they tie together. And the region on the surface isn't perfectly regular. Some of these chains penetrate out further than others do. The extended states in polyethylene all lie in the crystalline regions. For electrons, they lie along close to the polymer chain, but not in the chain itself. So they flow very easily at metallic type mobilities in these regions. When they come to the surface, the regularity is lost. There is a potential mismatch, and the electrons can get trapped on the chain bends, or they can move into the free volume region. Even if there's cavities, they can move into the cavities, and they can be trapped on molecules such as impurities, such as additives, because they will be concentrated in the amorphous region. The holes move along the chain. When they come to the surface, they're trapped there. I'll say a little bit about that. If there was no field, there's no preferred direction. So electrons that get inside the lamella can move back and forth. It's quite happy to do that. So can the holes. They will move back and forth along chain sections. If there's a field, then the field imposes a preferred direction, and just as the electrons get trapped in the surface, the holes will reside on these surface bends. The trapping energy is quite small, but the field forces them to line up in that region. In addition to these kind of traps, usually called physical traps, we have chemical traps. These are carbonyl groups, some residual double bonds in the chains, impurity molecules, cross-linking byproducts in cross-linked polyethylene. These hold the electron very strongly when they trap them. I've put here something about epoxy resins. We're not restricted to polyethylene. We're not restricted to semi-crystalline materials. This is an epoxy resin. Epoxy resins are made by having long polymer chains, usually with aromatic rings, sometimes with heteromolecules, sulfurs and so on in there. And there is an epoxide group at the end, which is used to cross-link to other chains using a hardening agent, in this case an amine. One amine molecule links 4 chains. It's not a nice, regular, rigid structure. It's a bit like a wobbly scaffold, the kind of thing I would put together. And this is roughly what you see. There is quite a bit of flexibility in these materials. The Extended states for electrons are usually through the cages. If they reach an aromatic ring, aromatic rings add electrons quite happily. They trap them electrons fairly strongly. These, under certain conditions, the amine crosslinks can trap holes. So here we've got the nature of the traps. This table is from calculations. Got a set of defects or impurity or chemical molecules, electron trap depth, hole trap depth, and these are calculated. Find that the physical traps are shallow, they're 0.3 eV or less. In chain defects, about half an electron volt, but molecules such as acetophenone, it's got an aromatic ring, it traps an electron very well. Alpha methylstyrene does the same thing, but cumyl alcohol is not very good, doesn't trap electrons or holes very well. Alpha methylstyrene traps a hole deeply, but only acetophenone only traps the hole in a shallow way. In aromatic resins, in epoxy resins, the aromatic groups, they act like acetophenone and they deep trap electrons, and in some circumstances, amine-like groups will deep trap holes. So these are the kind of traps we've got in these materials. Here is something I want you to think about. This is a photograph of the lamellar structure in copolymer of low-density polyethylene, high-density polyethylene. There are spherulites, high-density polyethylene spherulites, banded spherulites in low-density polyethylene. But put this together with the D-trapping times. For a trap depth of 0.3 eV, the residence time is 10 to the minus 8 of a second. That's terribly short. Half an electron volt, we're getting on to a few microseconds. 1 electron volt, we're anywhere days to months to years, depending upon how bound the electron is, or the charge carrier is, to the particular molecule. So what this means is that if we have electronic charge carriers that move rapidly through the lamella, it's as though they don't exist as regards the resistance of the material. When we come to the free volume and the lamellar surfaces, we've got traps like these. They sit there for a longer period of time, but it's not terribly long. It means that the charges can move reasonably rapidly along the surface of a lamella. So in the case where, in the situation where we're applying a field, and the lamella is angled with respect to the field, the charges will move on the lamella surface. The transport gets blocked when they have to move through the amorphous region, where they can encounter impurity molecules, where they can encounter cavities, where the free volume is bigger. The same kind of thing applies to the holes. They can move through the lamella. When they reach the lamellar surface, which is here, this is just, there's no amorphous region that you can see here. Every line is a lamella. When they reach the lamella surface, they have to move to a new chain, but the chains are close together. So, as we can see here on the surface, the chains are quite close together. So, if the field was allowing the carrier to move, it would move reasonably rapidly along the surface. Yeah, I forgot to mention this, but I will now. The charge we can substantiate these trap depths to some extent by using thermally stimulated currents, and we can certainly identify a range of traps with the similar energy levels. It's not really possible to do this, or not to do it very easily, using PA, because we usually only start to make measurements after about 30 seconds, 10 seconds. That already corresponds to deep traps. So, to come back here, the amorphous regions are the transport blockages for electronic carriers. But if we've got an ion, these are the only regions that they've got much chance of moving through. So this is the only region that the ions can move through. In fact, the ions are possibly found when the electrons or holes move into the amorphous regions. So the charge transport is a structured process if we go to the submicron scale. It's not homogeneous. Now, so far we've talked about the origin of the carriers. We've talked about how the carriers move. We haven't yet put it all together to relate it to what we measure as a current voltage characteristic. Current voltage characteristic, we're assuming that the current has reached a constant value for a given value of the field. A steady state. Everything that's going to change has changed. In order for that to occur, we have to have a dynamic equilibrium. What I've put here is say positive charge moving in at the anode and a positive charge being removed at the cathode, negative charge injected at the cathode being removed at the anode. And if we look at a typical part of the material, a volume element of the material, in general there's a large number of processes going on. We can trap the carriers, so the trapping retains the carriers. But we can detrap and release carriers. We can recombine positive and negative charges. So two ions, positive, negative ion, can recombine to give us a molecule, or positive or an electron and a hole can recombine, and we've lost our charge. But we can split them apart again and generate the carriers. So all those processes are going on. They've all got different time scales. They may all have different equations governing the way they work. In order for us to have dynamic equilibrium, we've got to have a situation where the net charge coming in on one side equals the net charge going out on the other side, and that applies for the electrodes as well. And as far as net charge is concerned, it doesn't matter whether that net charge is made up of electrons or holes or positive ions and negative ions or any combination, as long as we deal just with the net charge. There's one further point about this dynamic equilibrium. Very often we have traps at different energy levels, and it's assumed automatically, I think, that the probability of finding a charge in one level or another obeys either Boltzmann statistics or Fermi statistics. That presumes that the flow charge into that level equals the flow charge out of that level. It's called detailed balance, but it's not necessary to give a dynamic equilibrium. If we've reached a situation where the net charge flowing into any region equals the net charge flowing out of any region, then the current density is independent of position, and we've got a steady state. So this means that we've got to look at these processes. We want to know how the field affects the way these processes take place. Now, at low fields, crossing your fingers and a little prayer and a few other things as well, we can just about persuade ourselves that at the very least each of these processes are a linear function of the field. That's at low fields. It may not be true, but we can perhaps hope it is. When we come to high fields, that's not going to be true. We're going to get different field dependence for injection, maybe different field dependence for extraction, different field dependence for the way that the carriers move, perhaps different field dependence for mobile ions compared to mobile electrons. And then we've got all these processes as well. Now, to bring those into balance, into equilibrium, at the same applied field, we just have to be very lucky and it worked at one field. As soon as we change the field, we upset the balance. But nevertheless, we think, or it's presumed, that we do get a steady state. And the way we get it is that the imbalance between the current at different places, like the electrodes, as inside, perhaps even because of the internal structure in different regions inside, that imbalance generates space charge. The space charge acts to reduce the imbalance. And I'll come to that later, but before I deal with that point, we're going to look at the electrode processes. So these are very important, and they're not very well known. So, here I've taken from John Lewis's paper, a range of anode processes. And he's giving here 3 processes. Actually, number 3 is two processes rolled into one. Number 1 is the anode is positive. Electrons have come across the material to the anode. They have to be extracted. They're almost certainly trapped when they reach the anode. They have to be removed from the trap. They can tunnel into the anode, or they can be thermally promoted into the anode. We may have a negative molecular ion. So we've got to take the electron from the ion, and we usually probably reckon that this would go by tunnelling, but it doesn't have to. It could be thermal promotion. But there is something we have to remember about this. The neutral ion must be capable of independent existence. To give you an idea, let us think of OH minus. It's a nice negative ion. If I take the electron of OH minus, I can't have OH, it doesn't exist. So the only way this can happen is through chemistry, which will end up giving us water and hydrogen. No? Not so nice. Here is the third process. We've got to put positive charge in. After all, it is an anode. Now, one way we can do this, we can lift an electron from a state in the metal up to the metal Fermi energy. That leaves an empty state or a half-empty state down here, and I can take an electron from the valence bond. That gives me a hole which will move away from the anode. Oh no, that would be the normal way we think about it, and you should note that it costs energy. It's a thermally activated process. But there's also another process. If we have an electron coming into the anode, it gets taken into the anode, it has to drop down to the anode Fermi energy. That releases energy, and the energy is removed to promote this electron. So it allows hole injection, and it all happens in one go. It doesn't cost us energy, but because it's a number of processes acting together, it's not so probable. It's called an Auger process. Now, these processes are difficult to describe theoretically. We don't have nice mathematical expressions for them. So it's a big job to actually describe them, although people are starting to do that, particularly in Toulouse. Here's the cathode. Similar set of processes. Here's the metal. You can either thermally promote an electron, put it in a trap state, or even the conduction band, or you can tunnel it in to the polymer. Here, on number 2, you've got a positive ion. You've got to put an electron on that ion and neutralise it. And the same conditions apply. That neutral molecule has to have an existence, otherwise you have to do it by chemistry. And then here are 3 and 4. 3 allows you to neutralise hole by injecting an electron, either thermal promotion or tunnelling, to neutralise the hole. That is perfectly viable. And this one is the Auger process. You have a hole, it's neutralised, releases, there's an empty electron state here, electron drops down, releases energy, which is used to inject an electron. This one doesn't cost us energy, but it is a low probability process. Now, one of the things you should remember about these, there's nowhere here they take account of either contact charge, there's nowhere they take account of interface states. Some of these processes will behave differently if we have those kind of states present, that kind of charge present at the interface. Very little has been done in trying to describe that kind of situation. And here's a case in point. We always like to have a mathematical expression. This allows us to put numbers in and get a number out, and we can say, oh, it's big, I have to take account of it, or oh, it's small, I can forget it, or if I do this, I make it worse, or if I do that, I make it better. And it's relatively easy. It's now an important feature of models, computer models, for the generation of space charge. But there are problems associated with this kind of injection, the Schottky injection. Here's the metal. Here's the energy I would have to give an electron if I took it out of the metal. Again, leaving aside the contact charge, leaving aside any interface states. So there's an energy barrier to getting this charge into the material. If I make this metal a cathode, or the electron prefers to lie down the electric field, that will reduce the barrier for injection. And we get an expression for the current density given by this piece of mathematics here. This term here is the energy barrier that the electron or hole would have to surmount to get into the material if the field wasn't present. This part, this and that, gives us the reduction in the barrier due to the field. This bit, which is not always acted upon, tells us about the average speed of the electrons approaching the surface of the metal, and the fact that a proportion of them will actually be reflected and not penetrate the metal at all. So the pre-exponential factor has some importance. Now, what I'm saying down here, and you probably can't read that, is that this expression will only give us the field-dependent current that we observe in the steady state if it forces the bulk current density to match its value over a range of fields. So this process could be happening, but if it can't match the bulk current density, we can. So here we may have the Schottky injection taking place here, but if it cannot match the transport of the charge in the bulk, we either put more charge in than we can take away, or we take away more charge than we can put in, and we build up space charge, which modifies the field and brings us into an equilibrium. So it's not necessary that we should expect to observe this field dependence for the steady state current. Now, how on earth did that happen? All right, I knew there was something wrong here. Okay, I think we can see just about everything that we need to. Here are two examples where we observe Schottky injection. These points, they're experimental values. The data is taken from neutralizing injection of previously injected positive charge in epoxy resin. The X value is the field, and the field is measured from the space charge that we measure. The current is measured from the decrease of space charge that we measure. But these measurements were taken using equipment that measured on millisecond timescale, and this current is finished by the time we reach 10 seconds. Now, we get a nice fit. This is the square root of the field. We get a nice fit to the square root of the field. So we get a nice linear fit by plotting log of j against square root of e. But if you look at these factors here, none of them are disposable apart from the relative permittivity, which we know for the material concerned. So if we fit to a straight line, the value of ER we use in the fit has to be close to or equal to the value of the relative permittivity we measure for the material. Our value from the fit is 3.2. The value measured using dielectric spectroscopy is 3.4. So that's fairly good evidence for Schottky injection. That kind of evidence has been found by other workers in cross-linked polyethylene cable and in a high-density polyethylene 1986 by Yasuo Suzuki. So it's reasonably well attested. Here we have charge injection from a needle electrode into polyester. We're plotting not the log of the current, but the log of the light intensity, the light emission, because we know that that's proportional to the injected current. We don't know the space charge, so we're plotting the square root of the voltage. But we've got a very good straight line. This is a region of field where we would expect Schottky injection to occur. But of course it does produce space charge. These are not steady state equilibrium currents. Now, if we go to very high fields, and remember I've just shown you some data from a needle electrode experiment. If we go to very high fields, we can get a different kind of injection. We can get a tunneling injection. So here's the kind of field gradient you might, potential gradient you might get for typical experiment where we would see Schottky injection, make it higher, it reduces the barrier, but more importantly, it reduces the tunneling distance. Under those circumstances, we get this expression for the current density. So you can see that as the field gets bigger, the exponential gets closer to unity and the current gets higher. Phi here is the barrier for the electron in the absence of the electric field. In order that this apply, we need very high fields, at least 300 megavolts per meter or greater. So we really only expect to see it around needle-shaped electrodes in polymers. Sometimes we can get it in oxide dielectrics in thin layers. Now, here, there's a note that this is an approximate expression. It neglects the image charge. So it neglects this part and treats the potential as a potential like that. You can get numerical modifiers which convert this expression into one appropriate to an image charge. But neglecting the image charge actually is quite a severe approximation. Second approximation is, this is for 0 Kelvin. Takes no account of the effect of temperature. Here is what you get if you do an exact calculation. The calculation carried out for needle plane geometry. But all the processes are added up. So you add up tunneling, ground state tunneling, activated process for all activation energies. All of those are added up. And you get this line. That's the calculated line. Here's the Schottky expression. Now it's quite interesting. The Schottky expression has an approximate validity in this region of field. The calculation was for polyethylene, room temperature, and an activation difference in work functions of 1 electron volt. There's a point to note here. The Schottky injection is not 0 at 0 field. Now, this can't be true. We are not generating energy out of nothing. In fact, what's happened is that at 0 field, the system comes into a balance. And then when you apply the field, you disturb the balance. So the real calculation comes up like this. You could also disturb the balance by changing the temperature, hence thermionic emission. Here, this is the Schottky expression I just showed you with the triangular potential. That's a long way away from reality. But if we put the image charge in, we get a good fit at high fields, which is what we would expect. But for these kind of conditions, the region in which we do experiments is actually here. And it turns out that for a range of work function differences and temperatures, an expression of this form applies, but the coefficients are different for each case. So, even in the tractable mathematical form, these expressions are only approximate and can be quite well away from reality. We have evidence of Fowler-Nordheim injection in epoxy resin. Here the pin radius is very small. Here in this case 0.2 of a micron. The fields are really very high. Again, we're taking the log of the light emission rather than the log of the current density, dividing by the square of the voltage, and it should be proportional to 1 over the voltage, as we have here. In this case, the pin needle has an incredibly small tip, 0.8 microns, and you find 2 regions obeying the Fowler-Nordheim emission, and these are associated with different light emission, types of light emission, and this has got to do with 2 things. In one case, the proportionality constant between the pin voltage and the field has changed, and it's changed because here damage has occurred. Not yet a tree, very fine filamentary damage. Don't want to say any more about that. So those are the expressions for injection. Now, what about the number of carriers? Nobody's done any work yet on the field dependence, or very little work on the field dependence of contact charge injection. I think I had a paper at Winchester on that. but I don't want to labour that. Nobody's done any work on the field dependence of injection from interface states. But we can ask the question about donors and acceptors. Here's a molecule. It's got a donor level. In the absence of a field, we would have to give the electron this energy for it to escape from the molecule and be available to move through the material. When we put a field on the molecule, like this, the electron prefers energetically to be down the field, not up the field, and the barrier is reduced by a specific amount. We can work it out. Here's the total potential. We work out the position of the maximum in the potential, and from that we can find the reduction in the barrier. It takes this form. It's very similar to the Schottky injection. This is the excitation energy we would have to give it in the absence of a field. Mu is the mobility of the carrier once it's free. So it may have an activation energy, but that is probably going to be small. Once the carrier is free, it may move through the system by moving into neutral trap, then being lifted out of the trap and carried along, lifted out of the trap and carried along. In the presence of the field will reduce the barrier for the forward motion. It will increase the barrier for the reverse motion. So we end up with a mobility that has a form like this. This is the barrier in the absence of the field. The Cinch term effect represents the reduction of barrier for forward motion and a term for the reverse motion in which the barrier is increased. So there is a net forward flow given by this kind of expression, usually called the hopping expression. It will increase the carrier mobility. What we can see is that at low fields, so that this term is small, the Cinch term reduces essentially to this term, and the field in here cancels with the field down. So you reduce to the standard Mott expression for the mobility. When we have a high field, the first exponential term of the Cinch term dominates. So it increases, the mobility increases exponentially with the field. So now the question is, which of these processes dominate the transport of the carrier, or do none of them dominate? And this is a nice piece of work. It's data taken from a cross-linked polyethylene cable insulation during discharge, and the external current has been measured simultaneously with the space charge using the laser pressure pulse method. Now, the external current is a combination of two things. One is the conduction current. The second thing is the displacement of the space charge cloud in the material. By measuring these two features simultaneously, we can separate the space charge cloud movement from the conduction current movement. So what's been plotted here is the log of the conductivity, And this is the same set of data. The data is obtained at two different places within the material. And the field is determined from the space charge that we measure. Now, on this side, we've done a plot against the square root of field. Straight line should give you a Poole-Frankel transport. Remember, we removed the effect of the electrode from this experiment. The same data is plotted here, so it's exactly the same data, log of the conductivity against the field. Straight line here will give us the hopping conductivity expression. But if we look very carefully here, we have the same thing, same feature that we had with the Schottky injection. All these parameters are known. They're universal constants or known temperature. The only parameter that we've got that we can play around with is the relative permittivity. If we look at the hopping situation, we have an activation energy, but because we plot in log fashion, we can separate that. So, looking at the gradient of this plot, we've got the hopping distance. Those have got to be physically acceptable before we can say these expressions apply. And when we look at this, the Poole-Frankel plot, epsilon r is about 0.5. It should be 2.3. There is no way it should be less than 1. Well, you get a reasonably good straight line here. Not such a good straight line though. So it looks as though there's not a lot of evidence for the Poole-Frankel conduction. And Howard Wintle, in his Dakin lecture some years ago, presented a lot of argument that there is really no evidence for Poole-Frankel conduction in polymers. If you look at the hopping conduction, this is reasonable straight line. This is a bit better than that, but not terribly good. The hopping distance, 14 to 16 nanometers, is similar to the thickness of a lamella, so it's a possible candidate for the conduction, the transport process. But it's not really very good. So, on the balance of the evidence, we would have to say that neither of these two expressions, neither of these two processes really apply. And perhaps this is one of the reasons why. Already mentioned that space charge is going to modify things. If you have a current density in an applied field which changes from place to place, then it must build up space charge. And that's what's expressed here. If I've got a gradient in the current density, then more charge is coming into one area than is going out, so the space charge must increase in that area. And you only obtain a steady state situation when the current density becomes the same everywhere. The way that that happens is that the space charge gives a field gradient. The field gradient affects the current gradient to make this move to zero. This is the expression for current density in terms of carrier concentration, mobility, and here for generality I put negative carriers, positive carriers. Now, here is a situation, a case in point, experimental data. At 0 time, there's no space charge. This is a cable, mini cable. After 10,000 seconds, we've got some positive charge. After 20,000 seconds, you've got more positive charge. What happens to the field? This is a low field experiment, so we've only got 5 kV per millimetre on the system. This is the Laplace field. As the field, as we go across the cable, that we would expect if there was no space charge. As we get the space charge into the material, the field drops here, increases here. So since the current density is proportional to the field, it was high initially here, has been reduced. It was low initially here, it's been increased. We haven't yet reached the steady state, but you can see how the space charge can affect the situation. I promise that this is the only maths you're going to see in this talk, but there seems to be no way of getting around it. The standard way of looking at space charge and currents is to talk about space charge limited currents. In other words, the space charge limits the current. And it's to give you an idea of what is going on, I've done it in the simplest way. So there's only one type of carrier, no charge traps. So here's the current density, concentration of carrier, field. Here's Poisson's equation. Depends only on the concentration of the carrier. Forget the negative signs, it all comes out in the wash. If I now remove the concentration of carrier by making use of this expression, I end up with an equation like this. Remember, at steady state, the current density has to be constant. So there's no position dependence. J is a strict quantity. So once I've ended up at this expression, I can integrate and get an expression for the field in terms of all the other parameters, and that is here. So what we see is that the field increases as we go across the sample according to the square root of the distance. So it's doing something like that. X0 is a parameter. It's 0 if the field at the interface, the injecting electrode, is 0. X0 takes account of any situation in which that field is not reduced to 0. The carrier concentration is proportional to the inverse of the field. So, high carrier concentration close to the electrode, dropping down as you go across the material. Now, one of the things you should remember here, no traps. So this space charge is all made up of free electrons. They're held in place by the need to keep the current density constant. Once you've got the field, you can perform a second integration to get the current density in here as a function of the voltage and the thickness. And this is the expression we get. It's well known, it's in all the books. There are other assumptions. The electric field at the injecting electrode has to be low enough for injection to be independent of electrode field, and extraction is immediate upon the carrier reaching the electrode. So let's see what we get. Here it's a schematic diagram. Current density up here, voltage along there. We assume that we get an ohmic region at first. Then, if we had no traps, we'd move straight into this region up here. If we have traps, what happens is that only a fraction of the total charge, only a fraction of the total charge is available for transport. So we put a fraction in here, carry all the calculation through, and we end up with a situation in which only a fraction of the total charge is moving, but it depends upon the square of the voltage. If the traps are all at one energy, then the voltage reaches a specific value. There's a discontinuity as the traps are filled at that voltage, and we move over into the trap-free region. Here, so many electrons are being injected, all the traps are filled, and the current is overwhelmingly carried by the mobile fraction. Now, in reality, the traps aren't at one energy level, they're distributed, and what happens is that you get a slow movement from this region to eventually that region. The exact form of voltage or field dependence in here depends upon how those trap energy levels are distributed in energy. And they vary. If we've got an exponential distribution, this region is a power law, quite as high power law. If it's a uniform distribution between two limits, it's an exponential. And you can find anything, theory will give you anything in between. Now let me go back and say one thing further. I've limited this to one type of carrier. If we have both bipolar injection, positive and negative carriers, the space charge is determined by the difference between the numbers, the densities of those carriers. But the current is related to the sum of those carriers. This makes life very difficult. It's very difficult to solve mathematically. I can assure you that the standard texts in semiconductor physics run over something like 150 pages of various approximations that you can make, and we have no real justification for making any of those approximations. So let's come to what we know, or at least what we knew in 1988. Analysis of quite a few different polymers showed that the current density dependence could be split into a thermal dependence like this, with an activation energy, usually quite high. I've put here 1 electron volt. In the cable data that I've just shown you, it was about 1.8 electron volts. And a power of the voltage. Actually, a power of the field. This term is quite important. The power over the range from room temperature to about 60 degrees centigrade is effectively constant, and then it goes as 1 over T, the temperature. So, you can ask, is there any model that fits this behaviour? The nearest thing is an exponential distribution of traps. Calculations show you can have this exponential distribution. So it's got some justification. The current density then is predicted to be a mobility and a voltage to a power over a thickness to the same power plus 1. Doesn't matter how you play with the games with this, it always comes out like that. This power is what is proportional to 1 over t. So, in terms of voltage dependence, this looks quite reasonable, although there's no way that we can make a calculation which shows it being constant, independent of temperature. The thing that goes wrong is that we've always got one more power of distance than we got experimentally. Second thing is the mobility of the free carriers promoted up to some level here. You may expect that that has some thermal activation involved because there are no extended states in the polymers. But you wouldn't expect activation energies of this level, perhaps 0.3, 0.5. And as I said, the previous data that I showed you has values between 1.6 eV and 1.9 eV. This is, although it's attractive to think that this theory represents the data, in detail it doesn't. So, here we are. We have a model which is starting to get somewhere to explaining what goes on. The model injects carriers. It uses the Schottky expression with a modification to make sure that the injection current goes to 0 at 0 field. It injects both positive and negative charge and allows for recombination. It allows for recombination between trap positive and trap negative, and between a mobile charge and a trap charge. And you find that this plot here, that's the Schottky current. You find there are 3 regions. In this region, trapping reduces the mobile charge fraction. So, the injection is controlled by the trapped Homer charge to fit the bulk current controlled by the fraction of carriers that are mobile. In the centre, trap positive charge, trap negative charge overlap and they recombine. As we increase the field, we inject more charge, and the region of overlap between the trap charge gets bigger and bigger and bigger. Because they recombine, the space charge disappears from the centre, moves back to the electrodes. Now there's very little space charge. The current is controlled by injection at a value close to the applied field. That's what we're seeing here. This is following the Schottky behaviour. In here, the injection is so high that near to the electrodes we've filled the traps. The current is being carried by the mobile fraction near to the electrodes. The current is controlled by the bulk trap transport in a nearly trap-filled material. I talked to Christian about this, and he says it's not quite trap-filled, it's heading towards trap-filled behaviour. So here we are, we've got this kind of plot. Here's an experiment. I noticed Peter crept in just now, and he will recognise his own data. Okay, so it looks as though we got that. You know, everything's fine. We actually understand how we change around this system. Except we missed a few things. Even with bipolar injection, even with recombination, trapping, detrapping, the model does not give you heterocharge. This is experimental data. What you should know is that the capacitive, these data has been obtained during the application of the voltage, but the capacitive charge has been removed. So you're seeing the bulk charge and the image charge. This side is the cathode, but injects negative charge, reduces the cathode field. Some of that negative charge gets across to the anode, gives you negative heterocharge near to the anode, increases the anode field. This is not present in that very sophisticated model that I've just shown. Some time ago we were able to show this kind of thing happening partly reason why we get heterocharge. But it is, for those of you who measure space charge in these materials, it's quite a common feature. So now we come to the last topic of my talk. Charge packets. These were first observed, I think, some around about 1995. But I recently read through the chapter of our book, and there are hints in there that something like this was happening. However, we can say it was a bit of a shock to the system. It means that when you have a DC field, not everything stops moving, or rather, not everything keeps on moving uniformly. Here's some experiments. Well, let's give you some properties. I'm going to distinguish slow and fast charge packets here because we have to find a terminology. These were the ones that were first observed. They're activated. Their activation energy is about an electron or an electron volt or higher. The mobility here, 10 to the minus 16 meters squared per volt second, at 300 Kelvin. It's about the kind of value you would expect for a steady state carrier if you measured a steady state current. And they occur at applied fields in excess of 80 megavolts per meter. These are usually materials that have some chemical impurities. If you have rather good materials, it's higher. It's a higher value. Both these experiments are complementary, carried out at the same kinds of fields, on the same materials. Well, not the same individual samples, but the same materials. They're sections that are peeled from a cable that have been, in this case, I think, the cable hadn't been aged. What you see here is, at first, you just get negative charge coming across the sample. This is not a linear time base. That takes 48 hours. Most people don't have the patience to do PA measurements for longer than an hour. But let me tell you, there are some very interesting things if you sit around for long enough. And then it triggers a sequence of positive pulses. These are these yellow things. Now the thing about them is that for each pulse, the amount of charge, or the charge density amplitude, remains the same all the way across the sample until we start to extract it. The speed is constant. You can see these are straight lines. And now we come to the crunch, that it takes about, at this temperature, about 3.5 hours for this packet to cross 150 microns of material. When we finally get fed up and switch off the voltage, we find we've got a nice amount of heterocharge, both negative and positive heterocharge. So we've got packets that are repeated regularly. They need a heterocharge enhancement, in this case, to initiate a packet. We find that we need 140 megavolts per meter to initiate a packet. As long as the field at that electrode is 140 or higher, the packets will keep on coming. We did some clever measurements, altering the voltage to see when the packets would stop moving and so on, and we were never able to get this field back up to 140, and we didn't get any more packets. But we could take another sample, apply the same 120 megavolts per meter field, and get exactly the same result. In this case, the packet amplitude magnitude diminishes over time. It goes up very substantially between number 1 and number 2, but it slowly dies off. Here, a similar peeling, same cable, so same material, same cable, everything, measured with current simultaneously and light emission. What you find is a number of current pulses corresponding to the charge packets, and corresponding to those pulses are light emission bursts. It's assumed that the light emission is coming from the neutralization of the packet as it reaches the extracting electrode, and this may have an effect, may give us chemical degradation. That was the subject of the last Whitehead lecture. But we mustn't forget that the amount of charge in these packets is quite high. There is an electromechanical effect, compression and rarefaction, and this is repetitive. So we've got a fatiguing process going on at the same time as we might get chemical degradation. So there may be a route towards aging through such charged packets. The packet shape, we're usually using a one-dimensional measurement. Here, the measurement has been performed in 2 dimensions, and it has been shown that for this sample, the packet will start off as a uniform front, but start to break up. It's not always the case, but it can. So the front will split up. Maybe that's because there are local features in the morphology which will delay the movement of charge in one region compared to another. Now, there are a number of models for the formation of the slow packets. Their authors seem to consider them as competitive. I'll come to that in a minute. What we did with the packets that I have just shown you, these, we made a very thorough analysis as we could of features such as the speed of the packet at different temperatures, the residual charge, heterocharge, compared to the amount of charge in the packet, and so on. And we came to the conclusion that for our packets, the model that best fitted the behaviour was an ionisation plane moving through the material. In other words, the high field ionises impurity molecules, charge flows behind to one of the electrodes, the other charge is moving much slower, causes further ionisation, the charge then flows to the rear, recombines, and the ionisation front moves through the material. Under these circumstances, the speed is controlled by the mobile carrier in the average field. So it's independent of packet charge and location. In other words, there should be no change in the speed of the packet, just as we see here. The speed of the packet is the same, as it crosses the material. It's the same when you've got much less charge in there. The amplitude should be independent of position. I've already stated that. And here is the activation energy of the transit time. We luckily have 3 different temperatures. And here is the activation energy of the low field conductivity in the same material. You find that the activation energy is the same. So this is reasonable proof or reasonable validity for assuming that this model applies to those particular packets. And so I'll have a little bit more to say about that before I wrap up. Now, recently, we've found what we call fast charge packets. Now, the reason for this is the mobility is 6 orders of magnitude faster than the slow packets. To give you an idea, these packets cross 1.5 millimeters of insulation in less than a second at room temperature, as compared to 3.5 hours crossing time for 150 microns at room temperature. There are both positive and negative packets in the system at the same time. They occur at moderate fields, 20 to 50 megavolts per meter. They are thermally activated. Negative packet activation energy around 0.5 eV and is field dependent. Positive activation energy 0.23 eV and is essentially independent of field. And recently we've been able to identify the current pulses associated with these packets. There are many small current pulses. And these packets are delayed in their extraction, and they give a small amount of heterocharge, both positive and negative heterocharge, almost as soon as you've switched on the material, because the packets start very quickly and they travel very fast. So this is an important feature. What we've also been able to do is correlate the activation energies with mechanical relaxation in the material. Positive pulse activation energy is correlated with a gamma relaxation in cross-linked polyethylene, which is something like this. It's a kink, twists a very small part of the chain around 180 degrees, occurs in the amorphous phase. The negative pulses, I point out again, the activation energy field dependent, but it correlates with the activation energy of the beta relaxation. Again, this is in the amorphous phase. It correlates with, it's the relaxation that's associated with the glass transition, and opens and closes free volume. So the speculation is that the opening and closing of free volume is allowing the electrons to flow through this region in a correlated way. I don't want to go into that in any detail. Whereas the kink is moving part of a chain close to a neighbour so that reverse tunneling can transfer a hole. Now, I want to say just a little bit about attitudes rather than processes. As I say, I think there's grown up an idea that there is only one mechanism for this process. If my mechanism can reproduce a pulse and it fits my data, then it is the only mechanism. Now, when you look at the variety of properties that you see in charge packets, this seems to me to be no longer tenable. With the fast packets, I think this is agreed by all that it's a different phenomena. The activation energy is small, the onset field is small, and it's influenced by mechanical stress. You'll hear more about that tomorrow. But the three other models, or three I've shown here: ionization boundary, negative differential resistance, and a conductivity discontinuity. They all predict things which are somewhat different to one another. The activation energies seem to be rather similar. Fields at which you can get them are also rather similar. But here, the ionization boundary may initiate in the bulk. It may initiate close to the electrode. But as I said, the speed is constant, the amplitude is constant. Negative differential resistance should slow down on transit. And there are examples of this, but not every packet does this. The conductivity boundary stops in the bulk. This is a feature of the prediction. If your pulse doesn't stop in the bulk, it's not due to a conductivity boundary. So, in my opinion, there is more than one mechanism for the charge pulses. The mechanism that operates depends upon the conditions. Here you've got a range of condition systems. The mini cable, these are the fast pulses. The mechanism that we're suggesting is a charge compression boundary. Cross-link polyethylene peelings, we're suggesting an ionization plane. This one, not terribly sure yet. Oxidized cross-link polyethylene films, this seems to be an ionization. LDPE film, probably charge discontinuity, charge conduction discontinuity. We will get nowhere if we try to be too precious that our model explains everything. So where are we? Nearly finished, huh? Where are we now? We've got mathematically tractable models for steady state IV characteristics, but they're not sophisticated enough. Even when we include recombination, bipolar injection in a computer model, we cannot reproduce everything, or even the most common things that we see in experiment. The observed currents have a form that's unpredicted. This is what we've got as observed, and it should actually be field to the power n prime, not voltage. The source and the nature of the carriers is not completely clear. The carriers, when we measure a steady state current, we're very often looking at activation energies in excess of 1.5 electron volts. Are we really saying that we're taking electrons of chemical species? If you work out the time scale for that, we're talking about several years. Is it more likely that during those several years the charge stays on the molecule and the molecule goes through the material? People should be doing some work on this. And again, the interface states, how do they work? We can see a little bit about how they work, but we don't have any expressions. Bipolar injection is absolutely necessary. Nature of the interface needs more work. Go to the man's Eric Foster lecture tomorrow and find out all about the interface, huh? Carrier recombination, we cannot neglect it. It's there, and it may be also doing some damage for us. Relationship between current and space charge, it's not clear. We need more experiments. And we can do it. We can measure the space charge simultaneously with the current. We can ask the question, is this model, which was produced for semiconductors in the 1950s, does it really apply? The temperature dependence, space charge and currents, they're not well reproduced. One of the features you find about all these all-singing, all-dancing computer models, they fit perhaps two different experiments simultaneously. The conductivity experiment and the space charge experiment. But they fit it at one temperature. You change the temperature and the space charge is nothing like what you see. Charge packet theories. We need some more work. Fundamental work. Not, I've seen a charge packet and it does this, but I've tried to model the charge packet and I predict it does this. Electromechanical forces involved in fast charge packets. Giancarlo Montanari will say a little bit more about this tomorrow, but it's something you should think about. Polymers aren't nice crystals. Most of them are compressible. Even in epoxy resin is compressible compared to silicon crystal. This property can have quite an effect. If you read John Lewis's paper, he'll tell you some of the things that can happen because of that. And then, of course, you have to ask this kind of question. If you've got a steady-state DC current, do you ever get it at high fields? Well, I know it's finished. Last line. Does it ever occur? We may get a steady state of pulses, but do we ever get a current that is going to be constant? It's starting to look as though we don't get that. Perhaps the fast charge packets, perhaps that's what we usually regard as noise on the steady state current. So there we are. I think I'm to time.
You're very well on time. I think we've got a break for quarter of an hour.
Yeah.
I'm going to talk about nanodielectrics for about an hour or so. I won't keep you right until the end of the afternoon.